Welcome back. We're now moving on to 10.5, the solid state of matter. In this section, we're going to define and describe the bonding and properties of ionic, molecular, metallic, and covalent network crystalline solids. Describe the main types of crystalline solids: ionic solids, metallic solids, covalent network solids, and molecular solids. And explain the ways in which crystal defects can occur in a solid. You could make a drinking game into the number of times I just said solid. Don't do that if you're under 21. If you're over 21, be responsible. All right. So let's talk about the solid state of matter. Most liquids cool to freeze, and they end up forming these nice crystalline solids. When you go on to organic chemistry, if you're doing some extractions and recrystallization, you actually get to make these crystals, and they're really pretty watching them form. And just kind of some properties of these crystalline solids or crystals is the atoms, molecules, ions, whatever is in them are arranged in a definite repeating pattern. In general, metals and ionic compounds tend to form crystalline solids. The type of crystal or strength of it is classified by the forces that hold the different particles together that are in it. And we have four main types that we're going to talk about: ionic, metallic, covalent network, and molecular. It can happen where a liquid freezes before the particles can become arranged, and this causes what's called an amorphous solid, so no form solid, otherwise known as either a non-crystalline solid or glass. So if you have a substance with large molecules or mixtures of molecules that have very restricted movements, these are going to form these amorphous solids. And one example of that is candle wax. And though under certain conditions, you actually can make it so that the particles are ordered and they're able to transition to a crystalline structure. So here's kind of just a quick little example showing you a crystalline versus amorphous solid. The crystalline, you can see everything's ordered very nicely in there. There's a definite pattern, whereas the amorphous, the particles are all over the place. It's kind of like classroom versus virtual learning. Okay, and then here in B is showing also two different forms of silicon dioxide. In A, it is one of several crystalline forms. One of its forms is as quartz. Okay, so however, if you were to rapidly cool molten silicon dioxide, you get the amorphous form of it, which is also called fused silica. So in A, you can see this nice structure of silicon and two oxygens on each one, and they're alternating, and they've got this nice pattern, these nice hexagons forming, because nature and science love hexagons. Whereas in B, where you have the fused silica, this amorphous solid, there's no rhyme or reason to where things are going. So now we're going to jump into the types of solids, starting off with ionic solids. So these are composed of positive and negative ions held together by electrostatic attractions. And you're over here going, I know, Dr. Viz, we talked about this in like chapter 4. But we're going to talk even more about it and more in depth. Okay, so we talked about ionic compounds and a little bit about the solids that they form, that you don't just have an NaCl just by itself. It's in this cubic structure. So because of these strong attractions between the ions, you have the positive, full-on positive and negative charges attracted to each other, they have these very high melting points. So it takes a lot of energy to overcome those attractions. They're hard, but brittle. They shatter very easily. For example, sodium chloride table salt. If you have like rock salt, for instance, it's really easy to break it apart. You know, you might just like smash it with a hammer or something and it shatters. It doesn't bend. It doesn't do that. It just goes shoo all over the place. An interesting thing about them is the solids do not conduct electricity. So if you try to stick a light bulb with a positive and negative ends in it into solid sodium chloride, a whole lot of nothing's going to happen. But if you're able to melt it or you dissolve it in water, then it will conduct because now the ions are free to move around. So when they're in their solid form, the ions can't move, so they're not able to complete a cell. But when it's molten, they're able to move around because remember, in a liquid, the particles move. And then if they're dissolved, of course, they're able to move. We talked about what happens in the process of dissolution. The positive and negative charges separate and are floating around. And a lot of these ionic solids are made by reacting some type of metallic element, one of our metals, with a non-metallic element. And this forms, generally, a nice ionic compound with the properties of an ionic solid. Here's an example of what sodium chloride could look like if you could look at it on the atomic level. You've got these alternating sodium and chloride ions. Chloride tends to be, the anions tend to be bigger and the cations are smaller, so you can see them alternating and attracted to each other. The attraction happens in all directions evenly too. It's not just these two, sodium and chloride, are attracted to each other. The sodium is attracted to all these chlorides around it. Okay, and the chloride is attracted to all the sodiums around it. So the next type of solid is the metallic solid. And these are crystals that are formed by metal atoms. So what happens to describe this structure is you have this uniform distribution of the atomic nuclei, so all the metal nuclei, and you have a sea of delocalized electrons. So all the electrons are just kind of around, surrounding the whole system, floating around. Okay, and then they're held together, the atoms themselves, by a unique force that we call metallic bonding. That's all you need to know, is just the term. I'm not getting into it. That's something for advanced inorganic chemistry, which is a lot of fun, and something that's upper division chemistry. In general, our metallic solids, think about metals and their general bulk properties. They have high thermal and electrical conductivity, so they get hot fast, they conduct electricity. They have that pretty metallic luster. They're shiny, aka. They're malleable, so we can hammer them or make them change their form, adding a little bit of pressure. They're hard and strong. They do not shatter. Okay, you hit them with a hammer, they'll probably bend. Now, they have a whole wide range of melting points. Okay, for instance, you have mercury that's a liquid at room temperature, whereas every other metal is a solid. But something like gallium, only a little bit of heat melts it. Okay, and this is all due to the differences in strengths and the actual metallic bonding holding the atoms together. The stronger the metallic bonding that's happening, the higher the melting point. So here's an example. Copper is a metallic solid. So you have all these copper atoms, and the electrons are just kind of whooshing around in here, having a grand old time, making a sea of electrons. Our next type of solid is the covalent network solid. So some nonmetal crystals and covalent compounds can do this, not all of them. We'll talk about the next type of covalent solid in a second. So the covalent network solid. The atoms are being held together by a network of covalent bonds. Some examples of compounds that do this are diamond, silicon dioxide, aka sand, and silicon carbide, carborundum, which is what's used as the abrasive on sandpaper. To melt a covalent network solid, you have to actually break covalent bonds. So it takes a good amount of energy. For instance, these diamond, okay, so these covalent network solids are hard, okay, we characterize them based off of how hard they are, how strong they are, and what temperature they melt at. Diamond is one of the hardest substances known. You know, everyone wants a chainsaw or whatever that has diamond in it because it's great at scratching and cutting. It melts above 3,500 degrees Celsius. So it melts kind of like an ionic solid, very, very high melting point. So here's some examples of some covalent crystals. Diamond is on the far left there, so you can see that each of these carbons is covalently bonded to other carbons. Okay, so that's why it's a covalent network. You have a network of covalent bonds. Same goes for the silicon dioxide here. You see each silicon, even though it's SiO2 as the formula, they're all still covalently bonded with each other. And then same with silicon carbide, you have silicon and carbon. And then the last one is graphite, graphite, which is a little bit different. It's actually, these are planar sheets of graphite. It has these, and what graphite is made of carbon that's in these hexagonal rings. And then they're actually held together by non-covalent forces. So you have these sheets on top of each other. Graphite's really cool. You get to learn a lot about it in advanced inorganic chemistry. It's very soft and electrically conductive. So this is what's in your pencils. And the cool part is, one of the ways that it was discovered, well, actually graphene, which we'll talk about later, was by taking some sticky tape, basically, and removing layer by layer of it. And just sticking it on and taking it off. So next, molecular solids. These guys, there's not much to them. They're composed of neutral molecules. These are what we've talked about before, of covalent or molecular compounds. And they can have a whole wide range of attractive forces between the units, which leads to their large range of, apparently according to my spelling, melting points, aka melting points. So these don't actually form crystals. They're just there, okay? Each one, so carbon dioxide, each CO2 is its own entity. Same with iodine, each I2 is its own entity. Okay, so when it forms a solid, they all just come close together. They're not forming a crystal. I guess technically they're saying that they form somewhat crystalline solids, but not really. So let's talk about crystalline solids versus amorphous materials. Crystalline solids have very precise melting temperatures. So each atom or molecule that's of the same type is held in place with the same forces or energy. So that means it takes the same amount of energy to break the intermolecular forces, in one part of the crystal as it does in another part. So again, same amount of energy to break all of the attractions. So it's generally one temperature at which they're going to melt. Whereas amorphous materials are going to gradually soften over time because they have a variety of attractive forces since there's no pattern to them. So they end up having more of a melting range over a set of temperatures. Table 10.4 is from your book, and it looks at the types of crystalline solids and some of their properties, and just kind of brings everything together and summarizes it. I kind of hinted at graphite a little bit more. Diamond is super hard because of the super strong bonding between the carbon atoms in every single direction. Whereas graphite and pencil lead has very weak attractions between the carbon layers, which is why you can rub it off with your eraser. And you can see in the image of it, of graphite in the center here, there's kind of a long distance between the carbons. And then also, this is an actual, I believe this is an actual image of a graphite surface. And you can see that the centers of them are kind of far apart, which is why it's a little easier to erase them and break those attractions. Graphene is amazing. It is basically a single layer of graphite. And it's very, very helpful in things like semiconductor work, and it's got really cool properties. Let's see. It was actually first isolated in 2004 using tape to peel off thinner and thinner layers from graphite. So again, it's basically one atom thick layers of graphite. It's very, very strong and lightweight. It conducts electricity and heat very well. And so it's being used more in things like computer chips and circuits and batteries and solar cells and lighter structural materials. It's really cool. It can be manipulated into what are called Buckminster fullerenes, aka buckyballs, or into nanotubes. So if you hear of carbon nanotubes, it's graphene, or stack sheets, which makes graphite. Now, when it comes to defects, you can get defects occurring in crystalline solid patterns. So these can happen, you can have vacancies that occur when you have some positions that should contain atoms or ions and it's left vacant. So Sometimes the atoms or ions will get into these interstitial sites that are between regular positions for atoms. And this can actually be used to an advantage. Sometimes in a process called doping, impurities can be added to crystals, so they have these defects, and you can put an impurity in there. And this can create defects with things that we want. For instance, silicon crystals, they dope them with different elements to change their electrical properties to maybe give them a bigger band gap or smaller band gap for things like semiconductors and computer chips. And here's an example of a crystal with some defects. Shows a vacancy, an interstitial impurity. So you can see this interstitial impurity, this little dude here, is in between these little spaces for these atoms. And then we see a substitution impurity. This is taking the place of one of the teal atoms. And then we see also we can kind of make it distort depending on the substitution we add.